Hello and welcome back to digital signal processing. In this video, I'll explain sampling theorem and its matlab code. We all know any continuous signal can be represented in discrete form of the signal using samples. So what is sampling theorem? Now this sampling theorem specifies the maximum rate at which the continuous signal can be uniformly sampled so that the original signal can be reconstructed or recovered from these samples. So the sampling frequency always should be greater than or equal to 2 times of maximum highest frequency of the original signal. This is the condition to sample the continuous signal. Then only we can reconstruct or recover the original signal from these samples. And there should be also a minimum rate. So that minimum sampling rate that is allowed, f of s is 2 times of f of 1. So this is a minimum sampling rate. And this is a sampling rate at which the original signal can be recovered from the samples. And this minimum rate is called Nyquist's rate. Now, what happens if you sample the signal greater than the Nyquist rate and less than the Nyquist rate? Now, if we sample at a rate greater than the Nyquist rate, then this is called oversampling. This is called oversampling. And similarly, if f of s is less than the Nyquist rate times of f of n, then it is called undersampling. So sampling has 3 conditions. One, we can sample the signal at a rate f of s is equal to 2 times of f of m. This is the minimum sampling rate that is allowed. And the condition always must be to recover the signal, f of s should be greater than or equal to 2 times of f of m. If f of s is greater than 2 times of f of m, it is oversampling. And if f of s is less than 2 times of f of m, it is called undersampling. Now we'll write the MATLAB code and check what happens if we oversample or undersample a signal, or if we sample at the rate of the Nyquist stream, how the original signal can be reconstructed. So this is the sampling theorem. Let us go to MATLAB. Let us write the MATLAB code for the sampling theorem. So first let us consider the continuous signal. X is equal to continuous signal is nothing but a sinusoidal of the sine signal. We take the sinusoidal signal sine on 2 pi into f of n into 2. So we know that sine omega t is a sinusoidal signal. Omega is 2 pi f. Here f is t. Now we have to give the values for f of m and t. I'll take t as 1 and f of m as 4. And consider that. Now, for the scaling, because as t varies, x also varies. So for that, we'll take t1, this is t1, 0 to t, obviously, the x-axis goes from 0 to t. So now we have to consider the interval. For interval, I'll consider t by 100. So 0, 0.01, so up to t. So this is our original signal. Now, we'll check the sampling theorem. The first case, we'll consider the Nichols rate because, as I told you, it is the minimum sampling rate that is allowed. So that is f of s is equal to 2 into f of n. Now, we'll take the signal with the sampling rate y is equal to sine over again 2 pi into f of n into. Now, here we have to consider t s, that is 1 by f of s. But that I'll write instead of 1 by f of s, I'll write n, means I'll divide interval also, n by f of s. So what is the value of n? N will go from, we'll consider -1 with an interval of 0.1 to 1, right? So this is nothing but 1 by f of s t of s. So sine 2 pi fm into t of s, but we are using interval, right? Now we can plot the two plots, the original signal, subplot 2, 1, 1. We'll plot this original signal with respect to t comma x. Now we'll plot the signal with the sample. So subplot 2, 1, 2 stem, because it's a discrete signal. So we have to plot y with respect to n, because n is a value that is valid. Hold on, we'll plot onto the continuous signal. So hold on. Now, n, 1. Save and run. See here, this is our sinusoidal signal, and this is the sample signal, right? So this is the condition, right? Minimum sampling. So you can see the rate at which the original signal is sampled, and we can construct, because we can clearly see the values around to the continuous signal. So we can construct the original signal from these samples, right? Let us check the other conditions. Now here we have chosen the Nichols rate. Now I will choose the sampling rate as 3 times of. So as I told you, if f of s is greater than 2 times of fm, then it is called oversampling. Now we'll check this oversampling condition. What happens? So save and then run. So this is the oversampling time. We have to use 3 times of fm. So the number of samples will increase. Coming to the undersampling, so it should be less than 2 times of fm. So we take 1, 2. Then it is called undersampling. And then let us see what happens. We'll choose much lesser, 0.8. And then we'll check the graph again. Now we can see the number of samples. This is called undersampling. So if the samples are less than 2 times of fm, it is possible to reconstruct the signal, but we can construct the signal if it satisfies the registry. So the number of samples, we go for the more number of samples, then we'll get the exact signal. So that is the difference between the sampling, under sampling, and over sampling. I hope you all understood how to write the matlab code for sampling theorem. I will once again repeat what is called sampling theorem and how to write the matlab code. We all know that any continuous signal can be represented in its discrete form using samples. So there is a theorem which specifies the rate at which the continuous signal needs to be uniformly sampled so that the signal can be reconstructed or recovered from the sample. And that frequency is called sampling frequency, and f of s should be greater than or equal to 2 times of maximum highest frequency of the signal, f of m. So, and the minimum sampling rate is also there, that is allowed to construct the signal, and that is the Nicholas rate. So f of s is equal to 2 times of f of m. Now, what happens if we go for the sampling at the rate higher than the Nicholas rate and at the rate below the Nicholas rate? Then they are called oversampling if it is sampling is higher than the Nicholas rate, and if the sampling signal frequency is less than the Nicholas rate, then it is called under sampling. And we have seen the signal. So if we have more, sampling is nothing but the number of points that we consider on the original signal to reconstruction. The more number of points, the more accurate will be the signal. So that is condition that is the signal processing. How many samples we have to take to reconstruct the signal? That is called the sampling theorem, and that is the Nicholas rate. And we have learned about the undersampling and oversampling. What happens when we undersample or oversample the original signal? Whether what is the possibility of constructing and how the signal looks if we go for the undersamples for the oversamples. Sampling data. And it's matlab code. And in the code, we just have taken the continuous signal, which we want to convert into discrete signal. X is equal to sine 2 pi of T1. T1 is the interval. We have considered T as 1, and T1 goes from 0 to T with an interval of T pi 100. And the form M is, we have considered as 4. So X is equal to sine 2 pi of into T1. And then we have to consider the frequency. First, we have considered the Nicholas rate, then we change the rate that is less than 2 of them and greater than 2 of them. And then the next is we have to consider the signal at this sampling frequency. So again, write y is equal to sine 2 pi of into then we have write it as T of s. So T of s. T of s is nothing but 1 by f of s, and f of s we already considered. And here we have done the scaling with taking the values of n, which goes from -1 to 1 with the interval of 0.1. And then we plotted the original signal and also plotted the discrete signal on the original signal. So here we have to use stem to plot the samples and hold on and then plot on the continuous signal. Then we can see how the original signal is sampled. I hope you all understood.